Hello! In this video, I'd like to summarize the important topics from chapters 10.2 and 10.3 in your textbook on liquids and solids. I'd still like you to read the selections in the textbook, but here are the important topics you need to be aware of. Let's begin by talking about liquids. Question number 1, does a liquid have a definite volume? Well, the answer is yes. Liquids have a definite volume because the molecules in a liquid are very close together and therefore it's difficult to compress. There's not a whole lot of empty space between the particles. Does a liquid have a definite shape? No, as you know, the molecules in a liquid, because they are free to flow past one another, they can fill a container of any shape and therefore take the shape of that container. So, why would a given substance exist as a liquid rather than a gas? Well, as we talked about before, it has to do with the fact that in a liquid, the intermolecular attractive forces are stronger than in a gas. Now notice when we're talking about liquids, I'm referring to intermolecular attractive forces because for our purposes, liquids will always consist of molecular compounds. Now, let's talk about those intermolecular attractive forces. We're going to throw our minds back to chapter 6 when we learned how to predict the type and relative strength of intermolecular attractive forces based on the molecular geometry. So let us consider three molecules: methane, sulfur difluoride, and ammonia. For each of these, we will count the valence electrons, draw a Lewis structure, name the molecular geometry using VSEPR, determine whether the molecule is polar or nonpolar, and then name the most important intermolecular attractive forces. In methane, there's our Lewis structure with 4 bonds. We predict the geometry is tetrahedral. We know that a tetrahedral molecule is not polar, and therefore the most important intermolecular attractive forces are London dispersion forces. For sulfur tetrafluoride, an Ab2E2 type molecule, the molecular geometry is bent. Therefore, the molecule is polar, and the most important intermolecular attractive forces are dipole-dipole forces. For ammonia, an Ab3E type molecule, the geometry is trigonal pyramidal. Therefore, it is polar, but because of the presence of the NH bonds, we have hydrogen bonding as our most important intermolecular attractive force. So, I've listed these molecules from weaker to stronger intermolecular attractive forces. Now let's talk about some properties of liquids, and for most of these properties I will do a demonstration in class to show this. So, how does the density of a liquid compare to that of a gas? It is much denser than a gas, on the order of 1,000 times denser, and we can explain that because the particles, of course, are much closer together. As we said, the kinetic molecular theory of matter tells us that particles in a gas are very far apart from one another relative to their size. That is not the case in the liquid, so the density is much larger. Are liquids compressible? If I take a sample of a liquid in a cylinder with a piston on top and press down really, really hard, can I compress the liquid? Well, as we said, no. They are relatively incompressible, and as a result, the volume decreases only a tiny bit under high pressure. I cannot demonstrate this in class because I don't have the capacity to actually compress a liquid. Why would that be? Well, as we said before, that is because the molecules are very close to each other. There is very little empty space between them. Another property of liquids is diffusion. If I mix two different liquids, they will spread out and mix. I'll demonstrate this in class, but here's an example. If you put a few drops of a dye or food coloring in water, even without agitating it, after a while the liquid will diffuse and the color will appear to be uniform. Why is that? Well, just like a gas, the molecules are in constant random motion, and therefore they will eventually completely mix. Surface tension is a really interesting property of liquids. It is a force that pulls adjacent parts of the liquid surface together, causing the surface area to minimize. I will do several examples of this in class. One that you might have seen is this particular type of insect that can walk on the surface of water. Water, as we'll talk about in great detail, has very, very strong surface tension, and this insect can actually walk on the surface of water without breaking that surface tension. What is the source? As I said, very, very strong intermolecular attractive forces. And as we'll talk about in great detail, with water, that is hydrogen bonding. That is the particular type of intermolecular attractive force that gives water such unique properties. Capillary action is the attraction of a liquid to the surface of a solid that has a similar polarity. If they're both polar or both nonpolar, they are strongly attracted to each other. I will demonstrate this in class as well. Here's a picture I found on the internet. If you place a thin glass tube in a container of water, you will see that the water actually gets sucked up inside the tube because the water molecules are very strongly attracted to the polar surface of the glass. You can also see what we've observed before. This concavity is called a meniscus, and that's because the water is continuing to try to creep up the sides of the tube. And this is, as I said, because of the strong attraction of the water molecules to the glass surface. If I use a nonpolar liquid like mercury, we would actually have not capillary attraction, but capillary repulsion. You would see the mercury go down, and you would see a convexity instead of concavity. We will not do that demonstration in class, unfortunately. Now let's switch and talk about solids. Does a solid have a definite volume? Yes. As is the case with the liquid, the particles are very close together. There's almost no empty space between them, so they're difficult to compress. But does a solid have a definite shape? Yes, and that's because in a solid, the particles are not free to move about, so whatever shape it starts with, it stays that way unless you crush it or something. Why would a given substance exist as a solid rather than a liquid or gas? Well, obviously, because they have even stronger interparticle attractive forces, locking them into place and preventing them from moving about. Now, there are two major categories of solids that you should be aware of. Crystalline solids are solids in which the particles are arranged in an orderly, repeating geometric pattern. Does anybody remember the term we used back in Chapter 6 when we studied ionic bonding to talk about how the ions in an ionic solid are arranged? Yes, you got it. It's called a crystal lattice. So in a crystalline solid, there is a specific type of crystal lattice. The other major category are called amorphous solids. Amorphous means that they have no particular shape, and that's because the particles are arranged randomly. Here are some diagrams of some pictures. As you can see in the crystalline solid, those particles are packed in a regular repeating three-dimensional arrangement. In an amorphous solid, you can see that they're sort of distributed randomly. There are still strong interparticle attractive forces. It is still a solid, but they're not arranged in a crystal lattice. An intermediate category would be polycrystalline solids, where you have regions of crystallinity, but these regions are dispersed among one another. And I will show an example of each of these in class. Two very common examples, pretty much you see this in every textbook, would be quartz versus glass. Chemically, they're identical. They have the same empirical formula. They're both 2 moles of oxygen for 1 mole of silicon, but in quartz, they are arranged in a very regular three-dimensional arrangement in a crystal lattice, whereas if you melt the quartz and then freeze it quickly, you will have the amorphous structure of glass. Now, to go into a bit more detail, all crystalline solids have a crystal structure, which is the exact three-dimensional arrangement of the particles in a crystal lattice. The smallest portion of a crystal lattice that shows this three-dimensional pattern is called a unit cell. And even though I am not going to hold you accountable for the following information, I'm showing it in the video just because I think it's really cool. If you think of all the possible ways that you might arrange particles in a regular three-dimensional arrangement, there are really only 7 different crystal systems. And again, you do not need to know this, I just think it's really cool. Okay? Here are photographs taken from our textbook. The 7 different crystal systems in minerals include cubic, tetragonal, hexagonal, trigonal, orthorhombic, monoclinic, and triclinic. And you can see in this picture examples of gems and minerals that have these particular crystal systems. Now, let's finish up by talking about the types of crystals that exist. We can classify crystalline solids based on the type of particle that is present at each point in the crystal lattice and the interparticle forces that hold them together. So let's review all of these. Okay? In ionic crystals, like lithium chloride, the particle is obviously an ion, and the forces that hold the particles together would be, of course, ionic bonding, the electrostatic attraction between oppositely charged ions. An important category of solids are covalent network crystals. These are crystals in which you have a network of covalent bonds holding atoms together in a regular arrangement. What you see here is an example of diamond. A diamond is made up of simply carbon atoms that are bonded to 4 other carbon atoms in a tetrahedral arrangement by very strong covalent carbon-carbon bonds. So in a covalent network crystal, the particle at the point of the crystal lattice is an atom, and the attractive forces are covalent bonding. Metallic crystals, yes, metals can exist as crystals, are made up of metal atoms at the points in the crystal lattice, and of course the forces holding them together are considered metallic bonding. Again, we learned about that in Chapter 6. That's the mobile sea of electrons model. Finally, a covalent molecular crystal, and this would be an example of the crystal lattice of ice, water in the solid phase, is made up of molecules that are attracted by the intermolecular attractive forces that we know about. So the intermolecular attractive forces could, of course, be London dispersion forces, dipole-dipole forces, or hydrogen bonding, depending upon the polarity and the structure. In ice, you can see that the attractive forces are hydrogen bondings between the hydrogen atoms of one molecule and the oxygen of an adjacent one. And as we'll talk about later, this is exactly why ice is less dense than water. Okay, that's all we have to talk about. Have a nice day.